Okay, in this video, we're going to look at more limits at infinity. And I have three examples that I want to look at. And I'm going to go through kind of the long procedure to explain how the limit at infinity here works. And then don't worry, at the end, I'm going to show you a shortcut or see if you can kind of develop and see the shortcut on your own as we go through these three examples. The first one we have is the limit of 2x plus 5 divided by 3x squared plus 1. Now, we realize that if we try to use this direct substitution, if I plug infinity in for x, we would end up with infinity divided by infinity. And this here, recall, is one of our indeterminate forms. So that means here we should be able to rewrite this problem somehow. And the technique that I want to use is that we're going to look at the denominator and what is the largest variable x here that has what is the largest variable x here in the denominator? Well, in this case, we only have one, and the largest is x squared. So we're going to divide every term by x squared, because if you recall, if we have a fraction, if we multiply the numerator and the denominator by the same number, we do not change the expression. So we're going to take and divide everything by x squared. So that's 2x over x squared plus 5 over x squared all over 3x squared divided by x squared plus 1 over x squared. And now if we simplify, we have 2x over x squared. That will simplify to 2 over x. And then we leave the 5 over x squared. And the x squareds here on the bottom cancel, so we're left with 3. Then we have 1 over x squared. That remains 1 over x squared. Now, at this point, can we use our substitution? Well, if we plug infinity in, we're going to get 2 divided by infinity plus 5 over infinity squared, so that would be infinity, over 3 plus 1 over infinity. Well, from the previous video, we learned that 2 over infinity would be 0, 2 over a large number is 0, plus 5 over a large number is 0, and then we have the 3 plus 1 over a very large number also goes to 0. So now we're left with 0 divided by 3, which is simply 0. Okay? All right, let's look at the next example. And we're going to do the same procedure here. We have the limit of 2x squared plus 5 over 3x squared plus 1. And again, we're going to look in the denominator and take the variable with the largest exponent. So once again, that's going to be our x squared. And we're going to divide everything by x squared. Now, once again, why do we need to do this? Because if we try to plug infinity in, you're going to end up with 2 times infinity squared plus 5, 3 times infinity squared plus 1. So we're going to get infinity over infinity, which is our indeterminate form. So we're going to divide everything by x squared. Okay, now in doing so, what do we end up with when we simplify? Well, on top, x squared over x squared is going to cancel, so we will end up with 2 plus 5 over x squared. And this is over, again, on the bottom, the x squares cancel, so you're left with 3 plus 1 over x squared. And now if we actually take the limit, what's going to happen is as x approaches infinity for 2, again, that's a constant, so the 2 is going to remain 2. 5 over x squared will go to 0. The limit of 3 as x goes to 0, that's a constant, so that's going to remain 3. 1 over x squared, again, 1 over infinity, that's going to go to 0. So we're left with 2/3. Okay, so I think hopefully maybe you're starting to see a little bit of a pattern here, particularly if you look at this answer compared to the original problem. And if we look at one more example, once again, if we try to use the substitution here, we would get infinity on top, and we would also have infinity on the bottom. So we need to once again look at the denominator. And we have an x squared in the denominator, so that means we're going to divide everything by x squared. So we would have 2x cubed divided by x squared plus 5 over x squared. And on the bottom we'd have 3x squared over x squared plus 1 over x squared. And if we simplify each term, we have 2x cubed over x squared. That'll reduce to 2x plus 5 over x squared. And then the x squares cancel on the bottom, so we're left with 3 plus 1 over x squared. And at this point, if we use our substitution, if we plug in infinity, we would end up with 2 times x, so that's 2 times infinity, which would be infinity, plus 5 over infinity, well, 5 over a large number, once again, that's 0. And then on the bottom, the limit of 3 is going to remain 3, and the limit of 1 over x squared, we would end up with 1 over a large number, so that's equal to 0. So here we have infinity divided by 3. And what does that tell us? Well, that means this is going to infinity, which really tells us our limit does not exist. Now, once again, you might be able to look at the original problem here and see if you can make any kind of conclusion why this is going to infinity and therefore the limit does not exist. All right, now let's go up here and look at these 3 examples. If we look at the first example, look at the original problem, and let me see if you can determine how we come up with an answer of 0. If we compare the largest exponent in the numerator, which would be 2x to the first, to the largest exponent in the denominator, which would be our square. Okay, so we have a 1x to the first on top, x squared on the bottom, and we ended up with a limit of 0. And if we look at the next example, if we compare the largest exponent in the numerator, which is a 2, to the largest exponent in the denominator, which is also a 2, notice our answer is 2/3. Do we see a pattern yet? And if we look at the last one, we have 2x cubed, or we have an x cubed in the numerator, an x squared in the denominator, and our limit was infinity, so it does not exist. Okay, what's happening here, if you don't see the pattern, if we go up here and notice, if you look at the numerator and the denominator, if you compare the exponent, Notice we have an x to the first on top and x squared on the bottom. Well, if we kind of ignore everything else, because if we're looking at this problem going to infinity, multiplying by 2 really has no effect on the problem, and adding 5 has no effect, but we have the x on top. And if you're looking at x squared going to infinity here, the 3 and the 1 really have no major effect on the problem because we have infinity squared. Well, technically we have x over x squared. Well, infinity over infinity squared, here the denominator, because it's being squared, is growing faster to infinity, so it's getting larger at a faster rate than the numerator. So basically you have a number over a very large number, or you can think of it as a large number over an even bigger number. So therefore, just like the previous examples, our limit is going to go to 0. So anytime the exponent in the denominator is larger, your limit here will be 0 if you're taking the limit as x goes to infinity. Now, the next example, we have the same exponents on the numerator and the denominator. They're equal. If they are equal, then your answer is going to be the ratio of your coefficients, 2 over 3. So if you look at your limit, it's 2/3. And that's going to occur anytime the exponents in the top and the bottom are the same. And the last possibility is, what happens if the exponent in the numerator is larger than the exponent in the denominator? Well, this is kind of the reverse of what the first example was. Now the numerator is growing faster. You can think of this as infinity cubed. It's growing faster than infinity squared. So therefore, your limit is going to infinity. And because it's not approaching a number, it therefore does not exist. And you can notice here are the guidelines. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. And second, if the degree of the numerator is equal to the degree of the denominator, then the limit of your function is the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, the limit does not exist. And that is what is indicated with these 3 examples. So by knowing this, that means you can eliminate the process of going through all of this here where we're dividing by the x squared. You don't have to do that now. If you remember, you can simply compare the exponent with the numerator and the exponent in the denominator. So make sure you are familiar with and memorize these guidelines for finding limits at infinity, and that will make your limit process a lot easier.